Hello, everybody. Welcome to the Oceanology International session. This is on, I'll make sure I got the right title. We're on Hydrography, Geophysics and Geotechnics today. And we've got three speakers lined up for you. We have Dr. Mike Clare, who leads the Geohazards and Marine Sedimentology Research Group at the National Oceanography Centre in Southampton, UK. He formerly worked for 10 years as a geohazards consultant to offshore industries, having led Fugro's UK Engineering, Geology and Geohazard team. He's also currently the Marine Environmental Advisor for the International Cable Protection Committee. The next speaker will be Dave White. He's a professor at the University of Southampton on infrastructure geotechnics. He's based at the UK's National Infrastructure Laboratory at the Boulderwood Innovation Campus and has held this role since 2017. He began his research career in Cambridge with a PhD, then a lectureship, before moving to Australia, where he was based for 15 years at the University of Western Australia. His research is focused on geotechnics, in situ testing, and the design of cables, pipelines, and offshore foundations. He's authored more than 300 publications, which have received over 10,000 citations and 10 Best Paper Awards. He's active in engineering practice, consulting for the offshore industry, and writing contributions for API, ISO, and the DNV guidelines. He's an elected fellow of the ICE, the Royal Academy of Engineering, and the Royal Institution of Naval Architects, and also serves on the Society of Underwater Technology OSIG committee in the UK, coordinating the SUT two-day introductory course on geotopics and such like things in Southampton. And our final speaker will be Santiago Quinteros. He's a senior geotechnical engineer at the Norwegian Geotechnical Institute. Santiago works at the Department of Advanced Modelling and is also a doctoral researcher at Imperial College London. He obtained his bachelor's in civil engineering in Switzerland, then moved to Vancouver, Canada for his master's in geotechnical engineering. He has broad experience working both for industry and research in topics related to offshore engineering, field investigations, development of new technology and sensors, foundation design, earthquake geotechnical engineering, and advanced laboratory testing. He has international work experience in several countries, including Germany, Liechtenstein, Italy, Poland, Denmark, Ecuador, Russia, Norway, Switzerland, among others. So that's enough from me. We'll hand over now to our first speaker, who's Dr. Mike Clare.
Great. Okay. So, well, thanks for the opportunity to present here. I guess this presentation's largely going to follow on from presentations I've given at the last two versions of this session at Oceanology, where I've talked about seafloor geohazards, things like underwater landslides and avalanches of sand and mud that can break infrastructure such as cables and pipelines. We've talked about new approaches to making direct measurements of those geohazards and the insights that gives us into understanding the impacts on critical infrastructure and designing more resilient structures in future. This presentation is very much going to follow on from that and talk about some of the future developments and some of the very recent results that I and colleagues and collaborators have gained. And this is very much a collaborative author list here. This really want to recognize inputs from a number of different organizations. So when we're talking about seafloor geohazards, one of the obvious things that jumps out from kind of past experiences is large submarine landslides. So here the example in 1929, when a large magnitude earthquake, a magnitude 7 quake off the coast of Newfoundland, triggered a large submarine landslide, which started moving at several meters or tens of meters per second and started mixing with the ambient seawater to create a cloud or avalanche of sand and mud that we call a turbidity current. As this landslide became a turbidity current and moved down slope, it broke multiple cables, telecoms cables that connected North America through to the UK and Europe. And so we learned lots of things about how the ocean works and about how these processes work from this and from other early cable breaks at the turn of the last century. They told us something about how they were triggered, in some cases by large external events like earthquakes. They told us that these flows can run for hundreds of kilometers into the deep sea and breaking these cables on their way. And the times of these sequential breaks give us information about the frontal velocity of these flows as well. So there's a kind of a virtuous circle here between understanding more about how the ocean works, but also trying then to use those learnings to help inform how we design more resilient infrastructure. And it's not just landslides or turbidity currents that cause breaks. There are other natural processes as well. And while human-related breaks from anchors and fishing activities probably account for 90% of breaks on the global network, it's natural hazards that have the greater likelihood of breaking multiple cables in one region, which can be, in some cases, more significant. So here, just zooming in some of the locations where tropical cyclones have been recorded to break these cables. And in a kind of sin and post-COVID world, we've never been more reliant on this network that provides more than 99% of all digital data traffic. This is what keeps the internet going. So it's important to understand the hazards that affect these cabled networks. So we've actually gained quite a lot of understanding, particularly over the last decade, of how these different natural hazards work. Here's a paper that we presented in the Geological Society special publication earlier this year. This cartoon provides kind of a menu of different types and approaches of monitoring turbidity currents in the deep sea. Certainly over the last 5 to 10 years, there's been a real revolution in making direct measurements of natural hazards in the deep sea, such as turbidity currents, using cabled observatories, such as shown here in F, examples like the Venus Network offshore British Columbia, but also using novel moored deployments, some of which don't involve anchors actually being within the axis of the canyon where these flows are most powerful. And we can make measurements with things like acoustic Doppler current profilers, acquiring data at higher frequency than is usually gained for oceanographic purposes, and make measurements of the velocity, like vertically resolved velocity, and also acoustic backscatter, which is a proxy for sediment concentration. And it's these two parameters, the velocity and the sediment concentration in the flow, that we use to help understand what the impact forces are on structures such as pipelines. And in the bottom right here, I show an animation from John Hughes Clark from the Squamish Pro Delta. So in about 50 meters of water depth or thereabouts. And here we're looking upstream, looking up a submarine canyon, and we can see the Y to the high backscatter here. And we can see a turbidity current actually coming downstream towards us and interacting with bed forms here. It's sped up, but it's moving about 2.5 meters per second. And this is using a 500 kilohertz multi-beam echo sounder, like a fish finder. And others have extended that work. Here's some of the sea floor offshore from the Congo Canyon, so offshore the Congo River, in 2,000 meters water depth here. Chevron deployed an acoustic Doppler current profiler suspended about 85 meters above the seafloor, looking downwards, and remarkably found that during a monitoring window of 7 months, about a third of that time, a turbidity current was running down the Congo Canyon, moving at speeds of up to about 3 meters per second. So granted, this is the second biggest river in the world in terms of discharge, but this system was far more active than we thought. And in some cases, it looks like there's a traffic jam of turbidity currents going on. So we see these remarkable images that give us something about the internal anatomy of what a turbidity current actually looks like. We can get information about the velocity and see the head of the flow is actually the fastest part, moving about 2.5 meters per second. But some of the surprises that these flows can last several days. Some of the monitored flows lasted 10 days in duration, reaching thicknesses of up to about 100 meters and sustaining a velocity of about 1 meter per second for several days. So fascinating new insights at one point. And other places like the Monterey Canyon offshore California, this is work led by Charlie Paul and others at Monterey Bay Aquarium Research Institute, has taken that same sort of approach from the Congo Canyon, but has then looked at deploying multiple moorings, in this case at 6 different locations down the canyon. And we can track how these flows evolve in time and space and see in some sections where the canyons constrict and become narrower.
Yeah, that's fine.
So here we have these 6 moorings in the Monterey Canyon, and we can track how the velocity changes as the flow moves down the system, how the flows evolve, in some cases getting faster, in some cases transporting moorings down the canyon for several kilometers. And as they reach about 50 kilometers down the canyon and it broadens out, they start to slow down. So from this and a number of sites now, we're starting to make new measurements and starting to see what turbidity currents actually look like in the wild, how they behave, and make field scale measurements to test assumptions that we've made from scaled down laboratory models. The challenges are sometimes, though, that the flows don't do what we want them to. So in some cases, they damage or destroy, and we can lose moorings or instruments that are put in their path. And so this paper we published earlier this year showed some of the misadventures that I and collaborators have had, where turbidity currents have done a number of differing things to the moorings and instruments we've put in the way. Because the ADCPs are pinging at quite a fast rate and they're recording a lot of information that's depth resolved, they tend to be quite power and memory intensive. So we have a great reliance on expensive ship time, which really limits the kind of duration of the deployments that we can have. And the data's far from real time. We're typically waiting to go and recover the mooring unless we're looking at a system that's connected with a cable. So one of the things that we've been exploring is whether we can actually passively listen for the environmental noise that these natural hazards, landslides, and turbidity currents create. And can we place instruments that passively listen for these events and place the instruments out of harm's way? And certainly preliminary results seem to show that we can do that. And so this is data that's been processed by Steve Simmons at Hull University, looking at some of the monitoring data from the Monterey Canyon experiment offshore California. And so here in this top panel here, we show a time series of depth resolved velocity of a turbidity current. So we see the abrupt arrival here. The hot colors are faster velocities, several meters per second, and then decaying as we go through time. If we just zoom into this black box here, what Steve's done is to start to look at the noise that's generated by these turbidity currents. And what we see is a very similar shape to the noise profile as we do to the velocity profile with time. So it seems that we might actually be able to get some first order information about velocity from what these flows actually sound like. And these are acoustic signals generated by the turbidity currents at these multiple different moorings moving down to deeper water. John Hughes Clark and his student Hatcher et al. In 2017 went out to the Squamish Delta. This is a site that's pretty much geology on steroids, as John Hughes Clark would call it, where you get maybe 100 turbidity currents a season. And here they deployed a hydrophone as well as an acoustic Doppler current profiler, and identified that some fairly high frequency noise is generated by these turbidity currents. We can clearly see the arrival on the hydrophone of the turbidity current if we compare this to the water column multi-beam echo sounder data. So we get a really good idea of when these flows are arriving and initiating. And looking at regression of the acoustic noise that's being generated versus the current speed also seems to suggest that we should be able to get some kind of first order information from the noise that's generated about the speed of the flow. So this is quite exciting. And Gwyn Linton at the Canadian Geologic Survey has also been looking at hydrophone data deployed offshore from the Fraser River. So on the Fraser Delta, at the Delta Dynamics Laboratory on the Venus Network. And here he hears all sorts of different rumbles and noises, some low frequency noise that's attributed to submarine slope failures and collapses of the Delta, evidence of scour and erosion caused by turbidity currents. And those frequencies can also be discerned from vessel traffic and other environmental noise that's going on. So this is quite exciting because hydrophones don't use a lot of power. They don't generate very large data sizes. So if we can fingerprint and calibrate the data, we can use this passive acoustic detection to help us understand a whole range of different natural hazards. So we were very keen to take this to a much deeper site and take this to the Congo Canyon. And this is work led by Peter Talling at Durham University. So here the team have deployed a number of moorings from 1,000 meters water depth to almost 5,000 meters water depth, right down on the deep sea fan, to record the passage of turbidity currents. And here, remarkably, within just a few months, a turbidity current that ran out for 1,200 kilometers was recorded, actually speeding up about 1,000 kilometers from its source, reaching speeds in excess of 8 meters per second. Sadly, this flow caused every single one of the ADCPs to cut loose from its anchor and surface, but the surface times give us some indication of how fast the flow's moving. We've recovered the data from those, so there's some interesting information about how these flows are triggered. But the other really exciting thing is that hydrophones and ocean bottom seismometers, the same sorts of devices used to pick up earthquakes, were deployed on the terraces and the levees outside of the canyon. And the ocean bottom seismometers have very clearly picked up the arrival time and the noise of this turbidity current as it trucks its way all the way down to the submarine fan. So we're very interested at looking at those data, and it certainly appears like some of the other sites, there's different frequencies of noise that are presumably generated from the basal part of the turbidity current, which acts more like a sandy debris flow. So you hear the grain to grain interactions, as well as the more dilute upper part of the flow, which has a different noise. So with that in mind, if we can listen passively for these flows, we should be able to use acoustic sensing by other means, such as along fiber optic cables. So rather than just looking at the times of breaks to understand something about turbidity currents and seafloor hazards, can we use the backscattered energy, backscattered light along fiber optic cables to listen to the ocean environment? Well, we know we can do that because people are doing this commercially, to listen for traffic, for vessels and trawling activities. And there's a number of papers coming out in the last couple of years in particular from a number of groups, primarily out in the States, who've used these to detect near field and far field earthquakes. But also, this is work by Lindsay et al. From last year, looking at the Mars cable offshore Monterey Bay. They've detected a whole range of different processes at different frequencies and intensities that seem to point to the fact that distributed acoustic sensing using fiber optic cables should be able to detect things like scour events, turbidity currents, submarine landslides, and a range of oceanographic processes. So it seems very exciting. I guess the key things that need to be done in future are to get a more robust fingerprinting and calibration of those noises, so we can discern between different oceanographic processes, seismic processes. We're interested to lay these sorts of cables and put other devices into volcanic settings. But also, there's some interesting papers published in the last year looking at the quietening of the oceans during lockdowns. And those quiet periods provide us some new insights into the natural processes too. So I'll wrap up there. I think hopefully I've demonstrated over the last decade or so there's some big advances in geohazard monitoring. I think where we need to go next is looking at long endurance, low power networks, possibly using passive monitoring, and collaboration with cable networks, in situ cables that are there, and new bespoke cables, provide us a chance to build a global listening network, and in turn to provide information back to design more resilient infrastructure on the deep sea floor. So thank you.
Excellent. Thanks very much, Mike. Our next speaker will be Professor David White from the University of Southampton.
Now, hopefully you can all now see my slides as well. Yeah, bit of nodding. Excellent. Okay, so thanks for giving me the opportunity to speak, Steve, in this sort of reconvened online version of Oceanology International. And my presentation was part of a few presentations that were looking back, because this is 50 years or so since the first Oceanology. And the topic I'm going to focus on is in situ testing, and we're moving into geotechnics, which hopefully is exciting as Mike's geology on steroids, but we'll see how we go. And what I'm going to do is pick up on this theme of 50 years, but also make some risky predictions about the future. So what I'm going to do first of all is look at where we were 50 years ago when Oceanology began and what we were doing for in situ testing. Then I'll try and make a few comments about where some of those technologies have evolved, looking at present day advances and research. I'll then pick up on two interesting new challenges that have come up, looking at new things we're doing in the ocean and how we do in situ testing in geotechnics to face those challenges. And then I'll look at where this is all heading into the future. It's a team effort. There's a number of contributors across the bottom, including industry support on the right, and collaborators, particularly collaborators in Southampton and my former colleagues at the University of Western Australia. So 50 years ago, the easiest way in a short presentation like this to capture what we were doing 50 years ago is to look back at what was happening in the North Sea 50 years ago. And there's a great review paper by Bieram published sadly soon after his untimely early death, when he passed away after being the director of NGI. And NGI were leading a lot of the early work in the North Sea, and the key tools were the CPT, as shown here in his diagram from its paper, and then sampling via drilling with wireline sampling. So if we fast forward 50 years, unlike an awful lot of industries, we're still using pretty much the same tool. We've got CPTs as being our main device to gather characterization data, but maybe if I had to pick up one advance is that we're doing better at the process of integrating CPT data with geophysical data. So we're beginning to join the dots, if you like. So we've got 5 CPT profiles here from a paper by Southampton et al. Using some machine learning techniques pushed ahead by Mark Vardy, working with colleagues in NGI and other organizations. So what we can do now with our in situ tests is begin to make a better stab at joining the dots into the gaps between our CPTs. So on the right is some black data, which is the middle profile, and the green and orange are a machine learning technique trained on the geophysics, trained with some of the CPTs, making an estimate of the black data, and the green and orange are pretty good. So our CPT hasn't really changed much, but maybe what we're doing with it is intelligent and advancing with techniques like machine learning. Now let's move to 2 new challenges. So here are these 2 challenges. The questions are very simple. It's how much friction do we have on the sea floor? Now in this instance, we've got some soft clay with 2 pipelines which have been expanding and contracting, and unluckily they've both formed buckles heading towards each other. And so the question is, how is this going to continue in the future? And basically, how much friction are we getting from the soft clay on the seabed right at the surface, not at any depth? And then the second challenge here is a cable. Mike explained how important cables are these days, and these happen to be power cables going to a tidal turbine offshore the north coast of Scotland. The question here is, how stable are they on this seabed, which, as you can see, is extremely rugged, rocky seabed. So 2 questions: how much friction? So the in situ testing for friction on soft clay, well, traditional geotechnical practice is to take some box cores and then do sampling penetrometer tests up and down into the box core, which rather goes straight through the bit we're interested in. What we want is friction on the surface. But it's an important parameter to measure. Here's a database of drained interface friction angles for soft clays from around the world, and we see a huge variation. It doesn't correlate with plasticity index, unfortunately. And if we introduce the undrained friction that you get early in the life of a pipeline or during rapid movements, then the range would effectively be even higher. So it's a parameter that we really ought to measure, ideally in situ, or at least in a box core sample, minimizing disturbance, and we could do with a new tool. So here's a new tool. And this has come from the RIGS JIP, RIGS standing for Remote Intelligent Geotechnical Seabed Surveys. So this is supported by Fugro, Woodside, Shell, and Total. And this is Mark Schneider, excellent PhD student at UWA. And you see these devices move up and down. And then when they hit the seabed or the soil, they rotate. So the innovation here is really just that we're rotating while in a very controlled contact with the ground where the stress is monitored. And there's 3 different penetrometers shown here, all of which are a kind of shape that's suitable for going round and round. And even the toroid looks like a pipeline bent into a continuous circle. So they have pore pressure measurements, so you can do an effective stress analysis. And a test with one of these devices looks like this video here. So this is a video taken on a Fugro survey vessel offshore in a box core. And as we push the device in, we measure the undrained strength. We then wait for a dissipation test, just like a normal CPT, and that gives us the consolidation coefficient. And then we begin to rotate. And as it rotates, we measure initially the undrained interface strength, and then we slow down, move very slowly. And at the end of that period, we've also measured the drained interface friction. And then at the very end of the test, we pull the thing out, and that might give us some other data on the change in undrained strength. So we get pretty much all the parameters that we're interested in for pipeline and cable stability on soft clay from a relatively simple test that, depending on the soil, can be done relatively quickly. So that's an innovation as a kind of in situ test that's a better way for looking just at the very superficial soils. So that helps us with challenge 1. Challenge 2 is friction on rock. So here's the seabed bathymetry in the Pentland Firth with a bunch of cables running north-south towards the tidal turbines of the Maygen project over here. And the video that I showed earlier was a survey along the route of those cables. So friction of a cable on a rocky seabed is not really rocket science, and here's a very agricultural piece of equipment that drags something representing a cable over some rocks. And the friction goes up and down, sometimes the rocks break off, and the variations in friction are predominantly due to the local gradient that the cable is moving up and down on the ruggedness of the sea floor. So really the key to this is understanding the friction coefficient, imagining the horizontal or planar surfaces between rock and cable, but then you have to factor in the ruggedness, which creates this sort of uphill downhill movement, which can have a pretty big effect on the friction, perhaps doubling the effective friction that a cable gets on the kind of surface you see here. So we calibrated an uphill downhill friction model that gives you that accentuation of the friction from tests of this kind. And then we tried to then apply that to the bathymetry where we see the cable on this rocky seabed. Now, they've got some pretty good multi-beam echo sounder data of the Pentland Firth, but the bins are still not quite capturing some of the fine scale ruggedness that's there. So this is a pretty good indication, but it's at 25 centimeter or so resolution. Now, because we always have imagery from cable route surveys where you're checking for marine growth and other things, then you can do some image analysis to work out what size rocks actually are there, creating the fine scale ruggedness. You can then very laboriously create those rocks, as you see on the bottom right. And then once you've added that synthetic roughness, which is a pretty tough job, earning a PhD for Terry Griffiths down here, who's the author of this work. Once you've done that, you can then lay your cable, as you see here, on the synthetic ruggedness and then do a traditional stability analysis. So we've now got current and additional flows from waves. We've got the friction from the uphill downhill effect, and we can then assess the stability of the cable here. And the answer is going to be a much better or more, it's going to see more stability than if we had done traditional design practice, which is to just have a flat seabed and a simple friction coefficient represented by flat rock. So here's an illustration of the kind of results you get from that. And the way that I'm presenting this is plotting across the bottom here, the reaction force between the cable and the seabed as a distribution across the entire length of the cable that we just watched a little bit of video of. Now, if you have a flat seabed, that distribution is just 1 because the cable is applying its own weight, W, to the seabed along the whole length. But actually, once you have the ruggedness that we see, and if we use the multi-beam echo sounder, you see that about 7% of the cable is doing most of the work, carrying most of its own weight, with a distribution of stresses that is maybe typically 10 times the local weight of the cable, so concentrated loads over 7% of the cable length. But once you put the synthetic bathymetry on the top, actually only about 1% of the entire cable length is touching down, and therefore it's typically pressing down with about 100 times the unit weight per unit length of the cable. So this is quite a surprise when you first look at it, but it's then understandable when you go back to the video that the cable is resting on like a bed of nails kind of thing. When you do a stability calculation with this kind of information, you get a lot less lift because water can flow under the cable as well as over it, because most of the cable is in the air or in the water. You get less drag and you get much higher friction because of the effect that I showed beforehand. So what comes out of this is that if you introduce the detailed bathymetry on a rocky seabed, you can then capture the cable fluid seabed interaction better, and we then get a much higher factor of safety. These are the different design conditions, and if we go from the flat seabed to the multi-beam echo sounder bathymetry and then to the synthetic bathymetry, we get a huge jump in our calculated factor of safety each time. So what this sort of case study has shown us is that if we can quantify the small fine scale bathymetry as well as the friction coefficient of the rock, then putting those two together, we can find a more realistic assessment of cable stability that is a good news story. Cable is more stable. So to sort of wrap that up and see where that's going, well, really the geotechnics here really is meeting the hydrography, and it's all about understanding the fine scale bathymetry. So here's a little picture from movie from one of my colleagues, Blair Thornton, who does work on optical methods to get very high resolution bathymetry. And this is from a survey done out on the west coast of the US. And you can see here that the sort of techniques that we now have to measure bathymetry are down at sort of centimeter scale accuracy. And that allows you to unlock the improved cable stability assessments that I've been talking about. So to sort of wrap that up, what we've got is the two challenges I described, the friction on the very soft clay and the friction of the cable on the rock. And then the innovations here are a funny new kind of penetrometer, which doesn't just push straight through the soil, it pushes down and then rotates, and that's a better way to measure friction. This has now been used on maybe 6 different projects in maybe 3 or 4 different continents, and over 300 tests have been done. So that's a technology that's now out there to become commercialized, and Fugro is the contractor involved in that JIP who is looking at being the main route for that. Then on the right hand side, we've got cable stability on rock, and really the answer to understanding this better comes down to getting the bathymetry better rather than it being a geotechnical problem. And we've had support from JDR, the cable manufacturer, who've been involved in this, trying to push this forward as a guideline to influence practice. Okay, so these are both sort of technologies that if you could increase or make more easy gathering this data at the seabed, then we can push forward on a few different applications. So the question is, how do we widen the use of novel in situ testing? Now, to try to look forward, you could actually look back. So I've picked up 3 photos here from work in the early 80s. So this is an early ROV to perform CPT tests, cone penetrometer tests, which you see here. So this is lowered down to the seabed and does a CPT. And then this is a crewed submersible, people on board going down again to the seabed to do some CPTs. And these pictures are from a paper in 1983 by Joost Keizer and Harry Kolk, both of Fugro. So I've just reproduced their conclusion slide here because I think these read beautifully as a conclusion slide to predict the future today, even though they were written in 1983. So they basically say, we've got underwater vehicles, they already do some survey activity, but they could be used for geotechnics. They can provide a wealth of data if we do in situ testing from them, and we could include more equipment on these underwater vehicles. And that was 1983 at the time of the 13th Oceanology. So not worrying too much about the reasons, but certainly you could say that maybe we haven't made the progress that was envisaged when this paper was written back then. But there is some progress made. So we can look to some geotechnical sampling from an ROV, which happened last week at the time of recording this presentation. So here comes the vehicle down to the surface. We reach the surface and quickly deploy the sampler and gather a few hundred grams of geotechnical sample. The sampler deploys, it's successful, and everybody leaps up, celebrates, what a relief. And this is NASA sampling on the asteroid of Bennu, which is located 200 million miles from Earth. And there goes the vehicle flying away, bringing the sample back. And that will be in the lab in mid-2023. So, you know, not so good for a project timeline, but how are we doing in the offshore industry? So maybe we haven't quite got 200 million miles away, but maybe closer to home, we have been using ROVs to deploy CPTs. So this example on the left is widely used, a lot of projects by UTech, and there are others who are strapping CPTs onto the ROV. So that gives us more freedom to deploy CPTs without such a reliance on the vessel, but we're still tethered on the ROV. You can have fun doing this stuff in a low-cost way these days. Here's a ROV-based CPT that you could build and have change maybe from a £20 note if you did this, undergrads, having fun, looking at what you can do geotechnically from a small ROV. And then moving on the right-hand side, we take a further step out and we have an AUV to do missions that have some form of geotechnical involvement. And I like this picture. This is a suction caisson to tether an AUV to the seafloor, worked by cellular robotics. It's not really there for geotechnical investigation, but we're getting the idea that an AUV can interact with the seabed. And that brings all sorts of interesting questions. If you're going to use an AUV, the point is you're trying to save having the vessel there and the people, but there's a lot of decision making you might make during a offshore survey, a geotechnical survey, about what to do based on what data you've already got. So if we are going to take these steps of reducing the reliance on the surface vessel and using ROVs and maybe AUVs, it brings all sorts of questions about mission planning. Can I land? Should I land? Can I measure? Should I measure? Where should I go next? And so this is another topic which we're worrying about here in Southampton. So that brings me to the end. So there's the 4 questions I had at the start at the top. And I think the answers, it's a personal perspective, but I'd say maybe in situ testing offshore has evolved maybe rather slowly relative to other technologies and areas of the offshore industry and other industries. I've tried to highlight recently a couple of challenges that relate to the very surface of the seafloor, where there are some novel solutions that have been deployed and are useful in engineering practice, and they're finding their way into practice. And then I think what I've highlighted here is the enabling technologies that are affecting all areas really of life, and many areas of the offshore industry are listed here. And hopefully I've picked out a few examples where some of these technologies are finding a place. And what that's then enabling is us to do smarter in situ tests from platforms that are maybe more agile. They don't just involve pushing a pointed CPT into the ground. And that is giving us better data, better solutions for what we're trying to do. So I think that brings me to my conclusions. And I think I can hand on to the next speaker.
Excellent. Thanks very much, Dave. That was really good. So our last speaker is Santiago Quinteros.
Yeah. Okay, great. So I had quite a challenging topic for today. But first, thank you very much for the invitation and for the opportunity to talk today. I want to bring upon the future of the geotechnical laboratory testing and some possibilities on way forward. And more than trying to show fancy new devices or techniques, is first an alignment on the basics, where we are and we want to be in terms of commercial laboratory testing, not only for the research purpose, but the commercial part that we do for typical day-to-day industry projects. And then I'm gonna bring some ideas from also other new technologies that are arising and that we can use them in the future. So humans, we are animals of creating tools and using those tools all the time. And it's amazing how technology has evolved in the recent 1,000 years, but we can also be doomed by our own techniques and tools. We have created gunpowder in the 1900s and then nuclear weapons in the 40s. So we have to be wise what we develop and how we use those techniques and those tools, but also more attentive of how to use the tools across industries in use for the geotechnical develops and increasing those technologies for our use. But how could we predict the future? This is a very challenging question, actually. Other people have tried to predict future in the past, and from Victorian ages, it was thought that we will have one of those devices for flying around. Every single person has owned one of those, or even much more complicated ones. We're still not there yet. But also in transportation technology, we have made predictions and allegedly not gone quite as thought. Also, more allegedly good tools that we can use, like electric corsets. And this one is the one I prefer. The 1st of January 2000, of year 2000, everything should have collapsed. But it didn't happen. So it's quite challenging to predict the future. And I'm gonna just try to give a hint of the projects we are involved in and we would like to pursue at NGI as a commercial laboratory and also research laboratory, and the possible outcomes of that future. But to look into the future, we need to look into the past as well. So as NGI, we have performed many offshore projects, from the soil investigation, lab testing, to the design of the foundation and the instrumentation as well. So that has been the past, and the past has been concentrated on the energy that comes from gas and from oil. But certainly this should change. The type of energy we are consuming is not sustainable, and certainly this technology and the past lessons learned can be used into the development of the wind turbines or other sources of energy we will use in the future. In geotechnics, basically what we use is nothing else that all the devices that has been created in the range of the electromagnetic spectrum. So we create tools and techniques that measure waves in different forms, and then we bring it to the lab. And I think here is a beautiful summary from Carlos Santamarine on the ways or the techniques that we use in the geotechnical engineering, like mechanical waves, like bender elements, piezo pads, resonant columns, and so on, to get shear wave velocity and infirm also soil properties from liquefaction to stiffness. But also we use electromagnetic waves and thermal waves and the X-ray neutron. I'm going to talk a bit more about the last one because that's the one we think for the laboratory has or may have some input into the future techniques that we will develop. So as I told you, some alignment into the basic, what we would like to see across laboratory tests, then more that tools and techniques we are developing in irregular loading and partially drainage, autonomous lab testing, and virtual lab testing. So from the basic, the concept of relative density, how the soil is, or sandy granular soils is deposited into the ground in offshore engineering. Usually what you do is you make a laboratory test to determine your densest and your loosest states of the soil. And you calculate the so-called E-mean and E-max values of the soil. But there are several standards around and also proprietary laboratory procedures. And you usually have a huge scatter in the data you obtain. So that means that the relative density concept itself may be to be rethink, or that we agree among the laboratories to use only one way to do things, and we can calculate relative density more properly. So that means that the uncertainty right now is plus minus 20%, 25% on of the viewpoint of the relative density. If we continue using everywhere and all around the globe different laboratory setups to determine such parameters. Also, how do we treat our sands for reconstituting and in the laboratory? You can place a sand by moist damping, by wet pluviation, by dry pluviation, and you will end up with completely different stiffness, and also the friction angle can vary more than plus minus 2 degrees. So we should try to at least align on these basic concepts to have more certainty in the design we do. For trying at least to solve the last part on which reconstitution method you do, what we have done in the last years is freeze the ground, use a heat exchange unit and freeze inside in situ the ground, and get the sand out to the laboratory in a undisturbed way, or as undisturbed as possible as a frozen material. Then using X-ray technology by scanning your soil with an X-ray source and obtaining a 3D volume of the particles, then we can see the particle orientation, anisotropy, void ratio, and segregation, and try to see if any of the techniques for reconstituting your soil matches the frozen sand. So basically, if the particles are arranged in the way the frozen soil are also arranged, or in the way the void ratio across the specimens are the same as the frozen soil. So these are very basic concepts, fundamental and very basic. This is not complicated science, but still we are lacking a common understanding across laboratories to do the work properly, and also to bring clients a more secure way and also inexpensive way of building any wind turbines, for example. In the world of offshore, you have certainly many loads that are transient, that are not regular and not sinusoidal as the ones that you may have on a wind turbine. But those transient loads has to be considered when you're loading your soil, and especially in the frequency contents, because you can cause resonance of the structures. So for that, we have concentrated in a project with called WAX-XL to develop also techniques with irregular cyclic loading and the effect of partial drainage. That's the parts that we were considering. And that's my colleague Yusuke Suzuki that has been working heavily on these. So some of his slides and ideas. So in the terms of irregular loading, what we think is we should start seeing more of this irregular loading in the way that we are testing things for the industry and not idealizing sinusoidal curves for testing the sand, because you may be predicting your soil behavior quite badly. So you see the idealized behavior versus the irregular load behavior. So it has a significant impact on the way your average strains are basically captured. So you see that this is a thing that we would like to see in the future much more. Also, the effect of partially drainage, when you do an undrained test and a drain test, and then you start controlling the drainage in between, you will see that the stiffness increases and also the peak friction angles will be completely different. And that's just developing or using very, very simple technology with thin long tubes as flow resistance. And also now we are using metering valves, which allow you to also regulate the drainage of the cycles. So those simple tools and techniques we would like to see also in the future that can help you to understand better the behavior of the soil, because it plays a big role. The partially drainage conditions, we have a higher volumetric strain, obviously, but you see a significant different behavior in terms of pore water pressure of your soil when you cycle your soil as well. So those are the things that we would like to see much more use in future technology. Autonomous lab testing, that's also in the way that David was explaining. We have done amazing things in other planets, and here's a picture of a rover in Mars, like taking the first CPT, extraterrestrial CPT. And also we have nowadays, at least the technology is advancing, of self-driving cars. But it's still in the triaxial DSS or odometer testing in the laboratory is a lot of manual work. And we are pushing that technology here at NGI, especially now with the COVID issue, that we have to run experiments remotely. So how far can we push this? And that goes hand by hand by the sensors that you can have and the way that you can develop, putting cameras around your benches of the triaxial test to just follow up your test, and also do remoting valves closing and opening, and more advanced sensors that you will need. So in that way, we are also trying and using small sensoric in the nano and micro displacement control to be better in the transient loading or the cyclic loading application to your soil. And look around for new technologies and across the industries to get sensors that we could use in our day-to-day triaxial testing. Another topic that we are devoted to, and we think there is a huge potential, is actually the virtual laboratory one. And this has been inspired by the work done by Grenoble University, Sirujani, and also Caltech with Jose Andrade. And basically what we're doing here is creating a virtual lab of X-ray triaxial soils, a wide range of soil, from carbonate sands to tailings dams and all the offshore sands we find around. So we are scanning every single material that's passing through our lab from the offshore campaigns in granular materials. So this information is a 3D orientation, so the particles, contacts, and so on, that you can actually access afterwards and create avatar testing. So we have also developed an X-ray triaxial cell, a bigger one and a much more smaller one, as done in Grenoble. And we do also X-rays during a triaxial to see how the particles have been moved. What is the purpose of this? Why we're doing this extra work is as I say, inspired with the work that Caltech has done, you create your experimental image and then a virtual avatar with LSDM. So with DM, you can then capture the behavior of the experiment in a way, in a resolution that we don't have the access to. And you can see that the experiment and the simulation fit quite well. Now, if you have that, you can expand this in any direction, in any loading condition that in your commercial lab, usually you cannot. So you have a classic triaxial test that is done 60 years or plus, and the same ediometers, but you can not do stress pads that are completely, changing, rotating the principal stress of your soil. So for that purpose, we are devoted to use this virtual laboratory testing. So we have done for triaxial conditions and for monotonic testing, for example, drain, undrained, and you see that we capture the main features of the test, but then we can expand this to the cyclic loading. So we can do small cyclic amplitudes or larger cycles, and then it expand our lab capabilities. So this is not use of new machines or new techniques, but also the techniques that are across this industry that we can virtually merge to get better results and be more accurate in the way we can predict the soil behavior. So I think what I wanted just to show you was that there is work that needs to be done to align ourselves on the basics on laboratory testing. I just show you two examples in the way the relative density concept and the way we reconstitute our sand. And we should encourage more collaboration among the laboratory and open our databases, because there is huge potential to look into the past to learn for the future. Something we are doing here is irregular loading and the partial drainage, and we would like to see that because we see that's a potential for the industry for saving money there. Autonomous lab testing, how far can we really go? Can we do a lab test completely remotely, sitting here in Oslo and do a test in Perth or in Houston? That's something we are exploring. Virtual laboratory, that's a complementary expansion of the normal laboratory testing so that we can test also in different stress paths. But also we have to look in disruptive technology for use that and implement that in our day-to-day practice as well. So thank you very much. That was what I want to present to you. And I will hand you back.
Excellent. Thanks very much, Santiago. So 3 fascinating presentations, all covering different aspects of this offshore geotechnics, geophysics world. So because we're pre-recording this session, so we can't open it to questions and answers in the same way as we might normally do so. But I've got a couple of questions myself for the presenters, but also I'd encourage our 3 presenters to ask one another questions as well for the next few minutes. I've got one just to start off with for Mike. It's fascinating when you showed your slide about the hydrophone arrays in the Congo Canyon, and this huge breadth of data that's been gathered, for a whole multiplicity of sensors down there. And my curiosity there was, are those data sets in the public domain, or are these, behind a paywall? I'm thinking perhaps in terms of, we're just about to enter the UN decade on ocean science for sustainable development, and there's a huge amount of scope for African researchers there learning about their own backyard.
Yeah, I mean, it's a good question. I mean, as a NERC-funded researcher, part of our remit is making data available, open access and online. We actually haven't got our hands on all of the data yet because the field campaign's been going on during lockdown. So with the previous examples, like the Monterey Bay Aquarium Research Institute work in Monterey Canyon, those data are available open access. So the ADCP data are available with the publication. So the data for the Conga Canyon, the others will be available through the British Oceanographic Data Centre. And I think the hope with aligning with the decade of the ocean and looking at kind of new digital futures, that BODC portal will be able to host a bigger variety of data than it has done previously. Will make those data more accessible, because certainly one of the points that's come out from the two other presentations, and I didn't really touch on it, but is around machine learning and AI, is the data sets that we're gathering, whether they're ADCP, hydrophone, ocean bottom seismometer, they're very big, and we're hunting for events in them. Some of them, they're fairly specific events we're hunting for, big turbidity currents, but there's a lot of other value in there as well, of processes that operate within canyons that are of relevance and interest to oceanographers and biologists and other disciplines. So it's important that those data are shared, and it's important that they can be played with in a whole range of different ways, because there's a huge amount of just ocean noise that we don't understand that can be delved into. So once the data are back and we've actually tried to make some sense of them, then of course, yeah, they'll be shared via BODC, as would any other NERC funded project. And it's something else that we're keen, and we've been broadening out to other collaborators. It's where some of the folk in Newcastle University, Nick Wright and Jeff Neesham, who've been doing work on, listening for cetaceans and analyzing hydrophone data. We're applying some of their approaches. They're involved in this project to analyzing the data. So if people are interested to get involved, then do reach out, because we're very keen for a broader collaboration. I think one thing we've learned over the last few years is translation of other people's technology is particularly useful. And if somebody's already done it, then it's much easier to jump on top of that than it is to invent the wheel yourself.
Excellent. No, thanks, Mike. I'm reminded of in my studies, I remember us learning about when the USS Scorpion was lost, back in the 1960s, and how difficult it was for them to find the wreck of the submarine, with there being so few, acoustic arrays out in the Atlantic at the time. And in the end, they were able to find data, I believe, from the monitoring network for the Comprehensive Test Ban Treaty, in the end, that was detecting those in basically implosion sounds as the hull descended. And I understand similar techniques were used in the search for the missing Argentinian submarine a couple of years back as well. So no, fascinating stuff. And David, it was nice seeing the way that you'd reviewed the last 50 years as well, and seeing how in some aspects things aren't so different to to what they were back when I was a boy, and in other respects, there's some quite advanced technology going on. So what does your crystal ball say may be the big developments we're likely to see in coming years?
So I think crystal balls are very risky. I think if you look back, it's interesting, the first point you were making there, that some things haven't changed. It's interesting, I think, to look at reasons for that, and I think there's a number of possibilities there, and I think if we look back at those, it's useful to start then thinking about what may or may not happen in the future. And it's quite easy for people in research to say, oh, well, look at these amazing things you could do, but if there isn't a business driver for it to be developed, or if there's other non-science barriers. So, for example, the business drivers around reducing the reliance on vessels for an offshore survey is maybe something that is not going to be pursued by big players in that market, for example. The other one is around standardization, which everybody is involved in standardization, and I think Santiago's plot at the start is a fantastic example where standardization is not really present, even if we think it is, trying to rely on everybody producing the same kind of data. And a difficulty with standardization is that when you bring new technologies in, they may not be adopted, or very hard to get people to adopt. Even the little example I showed before of penetrometers going up and down, to get that out of the research lab into the commercial lab is really difficult, because the research labs themselves are very hard to produce data that projects will accept, because they're not certified in the same way as the commercial lab. And the commercial labs won't develop something if there isn't a market for it. So it's chicken and egg stuff. Yeah. So I think those are some of the obvious sort of barriers. So if you want to predict what's going to happen forward, I would always be so cautious, because that 1983 paper I picked up, which is just a conference paper by Fugro showing what they had done with some ROVs and some submersibles, they did that back then and had this vision that once we're untethered from a big survey vessel, then geotechnics can literally go burrowing around on the seabed, finding stuff out and sending the data back. And suddenly we maybe don't even need the lab. That would certainly help with project schedules. I think it's a bit flippant to imagine you would never need the lab. But if you can shift that balance to getting more data earlier in the field, then that's good for what we're trying to do. So I would think if I had to make predictions, then I would hope that we're going to move to use these technologies of robotics and low-cost sensing to try to get more data in situ in the field rather than relying on it when we get back to the lab. And I think if we can expand from pushing stuff straight up and down to doing more intelligent tests that represent more closely the stress histories and loading paths and the events that our infrastructure is going to see. So we're doing more like a model test. There's blurring the boundary between a model test and an element test. Then I think that could be quite exciting. And if you look at platforms for oceanographic data gathering that are used in other fields, then in geotechnics we should be trying to grab onto that technology as it's going ahead anyway, and see how we can adopt that for our technique. So I think that would be my attempt to look at some of the things that are going to happen in the future.
Okay, we'll come back to that in a mo. I just wanted first just to ask Santiago, a really interesting again presentation, mixture historical overview and trying to see the direction of travel into the future. One question I do have is calibration and validation side of things. As we do move into increasingly autonomous systems for going out there and obtaining data, to what extent can we rely on these robotic systems once they've been at sea for more than a few days or a few weeks to still be giving us reliable data? Is there a system that already on the horizon we might be able to use to test and calibrate?
Well, I think in that sense, we will have to do always not complete the calibrations, but at least a function check, as we call. And that's what we also do here in the lab. Every time you use a tool or whatever device, from a load cell to a LBDT or so, you do at least a function check to see if you are moving in a range that's acceptable as well. So that will at least assure you that you are not accessing data that's completely unrealistic to the expected values that you want to find into the field as well. So that could be at least a possible way to not introduce extra errors into the entire system. That may be a way forward for sure.
Okay, and perhaps this is a question for all of you: is the kind of policy and legal space as it needs to be for us to be able to operate all of these systems at the moment, or are there still changes needed in some marine legislation or working codes for this full adoption of robotic type systems?
I could maybe expand on what I was saying earlier around standardization, which I think creates difficulties if you're trying to use a different type of system to gather either the same type of data, so a CPT that's based on a small ROV or AUV or from an ASV, compared to a conventional system. You may find that you're not ticking every box of standardization, and so I think that's an obvious barrier, and that goes all the way up to people certifying and verifying their offshore platforms and offshore structures. So once you break the chain low down, you can have problems getting everything verified at the top. And I think that's sort of the tail wagging the dog around the way that we're set up. But it's a standardization is a difficult aspect to take on. I think there are also positives that you should look at. So the question of human risk, if you take people away from the offshore operations, then rather than worrying too much about the barriers, we should be making a big point about the savings, both in terms of reduced human risk, but also reduced fuel consumption and reduced equipment and other stuff. If we can use smaller and more agile platforms to reach the seafloor and investigate it. So I think we should look at the positive side. And I'm not a maritime lawyer, so I would struggle on answering the legal aspects of this all. But I think we should make a play for what the future could look like with the positive side, with the risk to human people and the environment. As you were saying earlier, Mike, I mean, your comment about being able to teleport into a research cruise for a day rather than having to sleep in a bunk for 6 weeks is a great benefit that we should be unlocking.
Although I don't know, sometimes if you've been working from home, then 6 weeks on a research vessel might be great. I think from a policy perspective, I mean, I touched on use of distributed acoustic sensing using in legacy or in situ fiber optic cables, and it opens up some interesting questions that I'm not qualified to answer. But you know, those cables, for example, in areas beyond national jurisdiction, are able to be laid and have freedom to lay because they're providing global communications links. If they're then being used as scientific instruments themselves, then potentially they're repurposed. So there are a lot of open questions around that, and around, say, the Smart Cables Joint Task Force project that's ongoing at the moment, looking at instrumenting or adding nodes, these green nodes to seafloor cables to make measurements of natural hazards, for tsunami warning systems, for monitoring the health of the oceans. That is interesting. And I think, you know, the collaboration between academia and industry is very strong there, but there are a number of kind of policy related challenges or legal challenges that face those sorts of global monitoring projects. And, you know, they're highlighted by ongoing things like the BBNJ instrument that's open at the moment. There are areas where I think there's future opportunities. You just got to make sure that the legislation that's put in place doesn't inhibit kind of societal benefits as well as preserving the health of the ocean. It's complicated. And I'm a geologist, so I'm not the person to solve that issue.
Yeah, and certainly that's an issue in the laboratory testing part as well. We know that several of the things we do here in the lab is basically not realistic at all of what we are most probably going to obtain in the field. But though we do them because we have to check the box for some, you know, standard or some way of feeling that is a requirement for one project. But we have to be more open that we could do things different and introduce new technology in the way we test the soil, but also that requires educated clients and educated engineers in the field that are open to apply those new technologies to new projects and then show to the whether authorities are reviewing that way the new technology and the new ways we're dealing with it we can use can be actually an open a huge potential to reducing the impact of, you know, in the monetary part, but also in the cost and the timeline of a project.
Yeah, no.
That is difficult. It's difficult.
So Santiago, you showed these amazing pictures that you know, the idea seems to be that you've got samples arriving in the lab. And do you think the future then could be that you simply scan the samples and then don't worry about testing them? And then the design process follows on from that scan, rather than at the moment we test them and then we really struggle to fit them to a constitutive model, and then we all get wrapped up there, and that makes things more tricky.
Yeah, I shouldn't say what I will say, but because it's our business, obviously we have to, you know, we're doing lab testing here, but we would like to move into a complementary, almost a transition between doing many things virtually. Just run the simulations that are less expensive. I mean, and computers are going to get better and better, and we can run an experiment in a few hours. And that's the point, to develop the constitutive parameters from a virtual part that we have previously calibrated with the lab, obviously, just to see if we are in ballpark right. And from there, open constitutive models that are inspiring the micromechanical behavior of the soil. That's exactly what we are pursuing. And we are trying to follow that line with testing, but that may kill our lab at the same time. Yeah.
Oh, it's fascinating, and it was really interesting what you were saying about the machine learning aspects. You know, very, very much what David's just raised. You know, once you recognize a particular pattern, it giving you a pretty good idea of what to expect from the physical characteristics of the of the sample. No, there's a lot of scope there. So let me open the floor to the three of you. Would you like to ask one another any questions?
Yeah, I had a question for Dave, and I guess also for Santiago as well. It's around scale, because you talked, Dave, about how important scale is to looking at bathymetry or friction. So it came back to the machine learning and the seismic inversion work that you presented. Obviously, the vertical resolution of the seismic data, even when you're getting to kind of the finer kind of chirp profiler data, it's not necessarily at the resolution that you would like. You know, it's not getting down to CPT resolution. It's not getting down to lab scale resolution. Like Santiago, it's not even the X-ray CT stuff. You know, you're talking about micro CT effects. How important is that, and how do you bridge that gap? Do you do it synthetically like you've done with a few case examples where you've got calibration, or how do you deal with it?
Yeah, it's this filling in the scale that you're right. So we have a gap in scale between what we currently do with physical tests, where we turn up in situ, and because we generally test by going straight down like this, we're actually not testing in the direction that's going to give us much understanding of the horizontal variability, but also we're testing in a different soil response to what we've often got in design for these problems that are near surface. So I think on the seismic side, which is not my expertise, then, as you say, systems like the chirp are getting higher resolution to delineate smaller features. I think on the in situ testing, there's more geotechnical side. The reason I like the platforms idea, so using low cost autonomous or remotely controlled vehicles, means it's much easier to start filling in the gaps. And if you've got some intelligence as you're doing this, so if your vehicle is coming along doing a smarter kind of CPT or some other funny penetrometer test, if you've got intelligence on the vehicle that can say, right, I'm using, let's say, the backscatter data or something, which I either already have or I'm gathering, then I can decide how often I need to stop on my journey and whether I need to stop more frequently now because I'm seeing changes in properties. Then I think once you get that, you start gathering data which resolves this problem of scale, because on the geotechnical side, you're refining your scale, while at the same time on the acoustic side, you're also converging towards the same point. So I quite like the vehicles. I quite like the low-cost tool idea, because I think also it comes to this idea that we were saying earlier, this is disruptive technologies that for some applications that are not a long way from shore, then it's possible for low-cost players, if you like, and undergraduate project students to have fun and make a contribution. Take an example locally here. So understanding the navigable depth in a dock or scour around a bridge pier doesn't have the big overhead of trying to do research out in the ocean, and it allows you to get going the idea of these much lower cost ways of investigating the seafloor or a riverbed or an estuary with a greater precision and with sort of smarter tools than we have at the moment. And that's a way to kind of get things going to then maybe them find their way to the further offshore. So does that answer your scale converging question, Mike?
I think so. I mean, I think you raised a good point there anyway. It's just even like things have come far. There's lots of technology, but there's data sets that you can use anyway that often people don't use, like the backscatter of the seafloor. The amount of surveys I've seen where the backscatter was recorded, but it's never provided to you is incredibly frustrating. So even just that making more of the data you have is and integrating better. I think that's what I took from your presentation particularly.
Yeah.
But you hit the nail with regard with the scale. That's true. I was hearing this talk representing the lab part, and basically we just take a tiny little sample and then we try to solve the world afterwards and create amazing constitutive models, and many of them with parameters that are not physically meaningful, and then we try to design our huge structure. So I think we have to play from several sides as well, not forget that we also the model testing needs to be done, and or also in situ testing of the more cost and more expensive also, but they are useful to just come back and see if our tiny little scale problem that we bring it into the lab is not actually chasing us at the end of the day. And yes, X-ray technology, you get at half a micron, and you go even further down. But the problem is that your sample got even ridiculously smaller, right? We're talking about that 11 millimeters diameter specimen versus a sea floor that is huge, and the wind turbines are getting also bigger and bigger. So yes, you hit the nail with that one. Mm-hmm.
Can I ask you, Mike? I mean, in your presentation of the hazards presented by two cables, a lot of your amazing technology you showed is about listening more carefully and understanding what's going to happen around them. Do we see these cables as poor, defenseless things where we just need to install more to make our global internet more robust, or are there scientific or engineering solutions to help our cables be robust when these geohazards present themselves?
It's a good question. I mean, I think in part, I should stress, I mean, the network is pretty resilient, and so there's a growth in use of kind of mesh type networks whereby you will reconnect at different places. So even if one part of your cable is broken, that you'll be able to do that. And it's an interesting industry because there's a lot of sharing of infrastructure between operators, unlike say oil and gas, for example, whereby multiple operators will be relying on the same network. There's been a big growth in understanding of actually how hazards are triggered and areas which are more prone to hazards. And so therefore routing strategies change as well. And so in that sense, there's not a huge amount of need there for changing the engineering, it's changing the routing. So previously it was thought you avoid high seismicity areas because they're going to be more prone to have submarine landslides than low seismicity areas. And actually the areas that have most of the kind of the breaks and the impacts of landslides and turbidity currents, it's where you have big sediment outflows from continents. So it's offshore from rivers and deltas. So avoiding those and going far enough offshore, choosing sections of canyon, if you have to cross it, where it's broader and the flows are going to expand and slow down, is more suitable. In terms of actually protecting the cable, I mean, there's some engineering work, but mostly it's still kind of a 17 to 21 mil diameter polyurethane cable. It's interesting. It's not the same as a pipeline. Often the kind of the bigger the diameter you give to it, the more area you give, and therefore the more drag there is. So mostly it's about trying to identify there are places where the cable will become buried and maybe will be protected. I think it would be interesting if we can make more measurements on cables, like looking at strumming, looking at loads on those cables to see what different mitigation measures will do. But that work in the field hasn't been done yet. There's a little bit of work in the laboratory. So I'd be quite keen to explore that sort of work. Yeah.
Mike, just out of curiosity, on the same line, actually, could we go wireless there? Could we go completely wireless? Even if not, could we also replace the material of the cables to make them more flexible or robust at the same time that we don't have to worry about?
I mean, at the moment, the bandwidth and security limitations are such that we still have more than 99% of all digital communications worldwide by cables. So we're not there yet. I mean, there are moves underway, but I think, chatting to people in telecoms, it looks like that's a way off. Cables are very much here to stay, and Facebook, Google, and others are laying their own cables to connect to data centers. There's interesting work and experiments being done by Microsoft in offshore data centers, which are apparently much more efficient for cooling the processing equipment. That will be interesting because that allows you to have hubs in the middle of the ocean potentially.
We're seeing a similar development there, Mike, in the defense sector as well. This idea about being able to have, obviously they want cables for their own listening purposes, and the idea now of being able to have subsea power hubs, self-contained recording units, so that you don't have to lay the cable all the way back to the shore, is very helpful for them as well. Yeah. One question I do have for you all is, obviously, we're living in a world where the ocean is getting warmer, sea level rise taking place, and presumably that's going to destabilize slopes as well. Thinking back to at the end of the last ice age, we know there's quite a lot of geological evidence of quite impressive slope failures and turbidity slides and such like. Particularly as we look at the high latitudes, in places like Greenland. Can we anticipate that, in coming decades, we may see an upturn in these kind of events that we need to have planned in advance for?
I think the thing that we can count on is that things are likely to change and be dynamic. Exactly which way they're going to go, the jury's out on. In terms of, I guess you're pointing to things like hydrate dissociation in high latitudes and potential destabilization. I think there was a time when it was very fashionable to attribute all submarine landslides to hydrate dissociation, as before that it was to link them all to earthquakes. I think now what we see is actually understanding the geotechnics is the most important thing, and is really looking at long-term preconditioning. So particularly muddy slopes where hydraulic conductivities are such that pore pressures can be maintained for long periods of time. It's areas that have received large sediment loads, so offshore from trough mouth fans, from receding ice sheets. That's the sort of areas where we should be anticipating more activity like that. I think what's clear is, for example, increased northern water freshening is driving bigger contrasts in temperature between, say, the North and the South Atlantic. That changes weather patterns. The UK is more rainy, the North Atlantic's going to become more stormy. And those sorts of things potentially could trigger more instabilities at the heads of canyons. It's probably not easy to say it's all going to become more likely, it's all going to become worse. We see changing patterns in the Pacific as tropical cyclone paths move poleward. So different areas that previously weren't affected by cyclones, which might in some cases be decreasing in intensity but slowing. In some areas get more rainfall, there's more discharge from, say, southern Taiwan. So I think we should certainly anticipate things to change, and we should anticipate the areas that have had greater sediment delivery might have less and others might have more. But it's complex, and the ocean obviously has a whole range of different feedbacks. It's something that the cable industry in particular is cognizant of, thinking of kind of the next 50 years, looking at landfalls which are going to be close to sea level, thinking about coastal erosion, failures of the shelf break. So I think the one thing we know is that things will change. Exactly how they'll change is going to be complicated.
Okay, excellent. That's good.
I think that message that change is something to have in mind applies not just for the natural environment, because of all the mechanisms you mentioned, both Steve and Mike, but also once you plonk infrastructure there, and also the fact that we now have infrastructure around the UK that's reaching the end of its life and is being decommissioned or repurposed, and the same thing will happen to offshore wind in a couple of decades. What we also beginning to recognise is that the condition of the ground around infrastructure is changing, and that can be both a good thing that helps design. So sediment delivery that covers and protects a cable, let's say, maybe moving it away from harmful loading, or scour around a wind turbine, which could be good, could be bad, depending on what the change in natural frequency is. All of these things should be acknowledged as part of the infrastructure having its own life, actually sort of changing. So the idea of being able to survey at the start, do a design and put that away, and then the infrastructure is there for 50 years, is perhaps, comes from the old way of doing design, whereas maybe now we should be more agile and think about properties changing. And so some of Santiago's lab tests that you showed are really amazing representations of the whole life of loading. And I think if we think about the same for in situ testing, so it's become routine a little bit to do in situ tests near the end of life through, for example, through drill cuttings, which weren't there at the start of the project, but their properties may matter sitting beneath the platform near the end of its life, or when it's being extended or something added. So I think this idea that properties change through life, as well as our climate and our environment changing, means that we should think about new ways of characterizing the seabed and monitoring it.
Excellent. Well said. Right. Anybody got anything else? Because it looks like we're coming up to the end of our time slot. I just have one quick supplemental question for you all. Of course, I'm utterly biased as the Chief Executive of the Society for Underwater Technology, but do you all see that they're in a world where we're all connected with, whether it's LinkedIn, Facebook, etc.? Do you still see that there is value in the role of the learning societies and the professional bodies for helping this community stay in touch and share and exchange new ideas?
I could go first really quick there, Steve. I mean, the message behind your right shoulder is behind all of the kind of discussions we had. We're geologists and geotechnical engineers, and talking about robotic technology and machine learning and so on. And none of us is expert across all of the things that have been touched on in today's session. So I think the things that the SUT organises and convenes are, of course, fantastic. Oceanology is a great place to hang out, to find out about these things.
Mm-hmm.
Great.
And I think it's amazing that we can share and have larger audience, as you pointed out also at the beginning. That's the good part, is that we can have a much broader publicum, but also share across many industries and many people as well. Videos. We are going to start producing videos here of the lab from the very beginning to the end, how you do and perform a laboratory that other people can use into the future. So, and post those online, and people can use it and self-educate themselves, so they don't necessarily need to go and read all the procedures and so on until they have a very good, a solid idea. And that also opens, I guess, a good way to criticism, and we can open the books among other laboratories and then show what we're doing, how we're doing, and that could be a very, very good outcome, that we are more exposed at the same time. But somehow we need to be connected too. COVID is making it a bit impossible to interact, but also at the same time we can interact across the oceans thanks to the cables.
Indeed, yes. It's wonderful to think that the reason we're even able to hold a meeting like this is because we have those fiber optic cables crisscrossing the global ocean floor, which is fantastic. Okay, anything from you, Mike? Otherwise, we'll need to
definitely echo
finish.
that, and I think societies such as SUT provide a really valuable role. I mean, I make sure that I stay grounded and listen to other disciplines' talks, and there's a chance to see what industry is being driven by versus just what's interesting and what's going on in the deepest depths of the ocean. The thing that needs to change is adapting to this current issue that we're in. But this is a great opportunity for societies to actually make sure that they do stay dynamic, that they do reach out. And I think one of the benefits is, rather than having an evening meeting or having to travel away, it allows for a more inclusive society in general. And it's something that is always very, very apparent. I mean, here we are, right? 4 guys chatting amongst ourselves, in terms of getting a diverse audience and putting great role models out for the next generations. It's important that the society keeps that in mind. And I think the online virtual side of things hopefully allows a more inclusive SUT and oceanology, and would like to see a kind of a more diverse cross section in 2 years' time.
Brilliant. Well said, Mike. And I know it's something that a lot of people are trying to work on. So thank you very much. Excellent having you all on board today. And we look forward to seeing you for real when when free movement is possible again. So thanks very much. Bye.
Thank you, Steve.